Problem 1 in the physics section asks us to solve for the period of this pendulum. And it'll also give us just the generic equation for period of all pendulums after this as well. But first, and this will go for most of the physics problems you'd study for, is you should make and write a few assumptions. I won't say this in every problem, but there are some things you just assume in physics that make the problem easier. Usually things like air resistance or frictionless surfaces, things like that, that would change the problem if they're implemented. We're not going to be doing math at a level that needs to implement those very complicated principles, but it is worth noting to your interviewee when you make big assumptions like that, just because it shows that you understand the difference between the real world and the simplified problem you're doing. So just for example, in this problem, some assumptions that we are going to make is, first, massless string. For most problems that have a string or a rope in it, or maybe a pulley system, you're going to assume massless string. It wouldn't make a massive difference, but if that string did have some sort of mass, your math would then change drastically. So second thing we're going to assume is that this pendulum is going to be swinging in simple harmonic motion. Our third assumption is that the mass itself is going to become a point mass. Most assumptions, most physics problems, the object that you're considering you assume to be a point mass is. If you drop a car off a cliff, you are just assuming it is a specific point that all of that mass is generalized. You don't have to worry about center of mass or center of gravity or anything like that. It's just a single point in space with all of the mass and properties associated with it. And then our last assumption is that the theta that our pendulum is swinging is going to be small. This allows us to make a few mathematic assumptions about when we use our trig functions later on. So the next thing we want to do for this problem is we're just going to do a free body diagram, and we're going to annotate all the forces that are acting on our bob here. So I've gone ahead and drawn out our free body diagram here. And just some things I want to highlight is there's only two forces. We have tension, which is always pulling towards the fixed point of our pendulum, and then the force due to gravity, which is always pointing directly downwards. So we can break up gravity into its two components, as I've done here, to match tension, to match the same coordinate system that I'm putting tension on, this red XY coordinate system. Next, we can draw out our force equation. So we know that the sum of any force equals mass times acceleration. So if we look in our y direction, our red y direction, I know the sum of our forces in those y directions equals, if we say positive is upwards, tension minus just the component of gravity in the y direction. And that's going to equal 0 because there's no acceleration away from or towards the focal point. And so we know that tension is always going to equal the force due to gravity in the y direction. Next, and more importantly, we have the force in the x direction. And so what this is going to equal is simply the force due to gravity in the x direction. And that is going to equal some mass times acceleration. But what we also know, an assumption that we can make, is because this is simple harmonic motion, that this force due to gravity in the x direction is acting like some restoring force. Something that is essentially trying to bring it back to some neutral position. So our formula for the force due to gravity in the x direction is we can solve with trig. So we know that we're looking for this component right here, and we know this angle and therefore this interior angle. We can solve using sine of theta, which equals the opposite over hypotenuse. We know that sine of theta equals fgx divided by fg, and therefore fgx equals fg, the force due to gravity, times sine of theta. And simplifying this, we know it's mass times the acceleration due to gravity times sine theta. So we can plug this in on the left side of the equation, getting mass times g times sine theta. And we also know that the restoring force equation is equal to x times k, where x is some distance and k is the restoring constant. Usually you see this in like a spring, where k is the spring constant and x is the displaced distance from that equilibrium point. Right now it's just going to be some constant, not a spring constant specifically. So from this point we can solve for k, and we're going to get mg sine theta over x. Now, what you can do from here is we're going to make our first assumption. We're going to utilize one of our first assumptions. So we know that sine of theta is approximately theta when theta is small angles, usually about 10 degrees. So we can substitute this into our new equation. We get mg times theta. But another step that we can make is we know that x is equal to the length of the string times sine theta. Right? You can see that if you see that this length of the string here is this diagonal hypotenuse and you have x right here, we can basically make the same assumption where sine of use the same equation where sine equals opposite over hypotenuse, or x over L, and you can solve for x equals length times sine theta. And now if we come back down here, we have that equation that we just wrote, but we can use the same approximation and get x equals length times theta. And if we just plug that in right here, we get length times theta. These two thetas are going to cancel out, and we get left with k equals mass times acceleration due to gravity over length of our pendulum. From this point, we're going to use the simple harmonic motion equation, which we know is 2 pi times the mass over the constant. Right? And again, you see this sort of thing when you're looking at a spring and it's wobbling back and forth. M being the mass of whatever the bob is, K being the spring constant. But here, we can now plug in our constant that we just found, and we're going to get m over mg over L, and all of this is going to equal 2 pi L over g. And we get the period of a pendulum to be 2 pi times the square root of the length of the pendulum times the acceleration due to gravity.